Well, let's go through some boring theorems concerning limits. This theorem 1 is the following. Suppose that we have some function which is described by its real value and its imaginary value. As usual, we call these real and imaginary values u and v respectively. And let's consider one particular point in the complex plane, which we call set 0. It consists of a real part x0 and an imaginary part y0. And this point is mapped to a point w0, which has this real part and this imaginary part. So here we have some point in the range of this function. And we are now going to consider the limit f of set when set approach set 0. And we call this w0, and the theorem says the following, that this limit exists if and only if the limits of each of the components, the real components and the imaginary components of f of set, if the corresponding limits of these functions exists. So this means that any point x, y is approaching this point x0, y0. And we call this limit u0 if it exists. And similarly, we define the imaginary part of this function. We say that the limit of this function is equal to v0, exactly in the same manner as for the real part. So the theorem says that if these two limits exist, then the limit of the complex function f of set is equal to w0. This limit also exists, and vice versa. We also have a second theorem here. Suppose that this limit, which we called small w0, exists. And we also assume that we have some other function which we call capital F of set, and that the corresponding limit of this function exists when set approaches the same point set 0. Then it does not come as a surprise for you that the limit of the sum of these two functions are what you should expect, that the limit of this sum is equal to the sum of the corresponding limits. In the same way, if we want to take the limit of the product of these functions, then this limit would be, not surprisingly, the limit of each of these functions multiplied with each other. And in the same way for a fraction, if you take this small f of set and divide it to the capital F of set, then this limit exists and it's equal to the limit of the first function divided to the second function. In this case, we have to assume that the limit of f of set, this capital W0, is different from 0. Otherwise, we get a 0 in the denominator, which is not very good. A corollary, some immediately application of this theorem is the following. Any polynomial f of set has a property that the limit of this polynomial exist for any point set 0. It's really trivial to see this from the above theorem. Let's turn to the limit of the absolute value. It's possible to prove, it's not difficult at all, we shall not do it. It's possible to prove that if the limit of f of z is equal to w0, we denoted this, and that this exists, then the limit of the absolute value, which is a real function actually, will be equal to the absolute value of the limit w0. This is, we turn now to a definition. We say that lim of f of z when z approaches z0 is equal to infinity if the limit of the absolute value of f of z is equal to infinity. An example of this is the following. We have this fraction, and we easily see that when z approaches -1, then we approaching 0 in the denominator, and of course this limit will be equal to 0 at to infinity, because the denominator is bounded. Let's now turn to the definition of continuity. The continuity is very close to the definition of limits. We say that a function f of z is continuous at a point z0 if the limit f of z as z approaches z0 exists, that the function value in this point exists, and that the limit of the function as z goes to z0 is equal to the function value in this point.